Assalamualaikum. Today I will talk about our project heat conduction through a metal ball. We have two tasks for this assignment. For question number 1 and 2, we have to create a video presentation. How to use mathematical software to obtain the solution and explain our result. So, for question number 1, we are given 1D heat equation, which is this, where K is called the diffusivity of the metal ball. The question given boundary, initiality, and we have to show that AN equal to 0 and BN equal to 2 over L integrate 0 to L function of sine lambda n x in term of x. So if we use the properties from the note, we will get a simple calculation from chapter 3 Fourier series. If the function given is an odd function, so from the properties of odd function, we have a naught equal to an equal to 0. So we can substitute a naught and an into this equation. So we will get uxt equal to bn sine lambda n x exponent negative lambda n kt. So in order to find Bn, if a function is defined on interval x between 0 and L, then it has Fourier sine series of Bn equal to 2 over L integrate 0 to L function sine n pi x over L in term of x. Okay, we have our interval which is x between 0 to L. So we can get our Bn equal to 2 over L integrate 0 L function sine lambda n x in term of x, which is n equal to 0, 1, 2, and so on. Okay. So we have shown that A naught equal to 0 and Bn equal to this equation. So we have to solve this equation using solving linear partial differential equation. So we have the first equation, which is delta u over delta t equal to k delta squared u equal over delta x squared. Then we have the differentiate u and differentiate t. We also find double differentiate, and we have to substitute delta u over delta t and delta squared u over delta x squared into our first equation. Then we can get this equation. Then we have to divide it with k. After we divide with k, so we can get the equation equal to negative lambda. And we can let negative lambda equal to 2 and x double prime x lambda x equal to 0 as equation number 3. Okay, so for equation number 3, we consider case 1, case 2, and case 3. For case 1, we have lambda equal to 0. Then we have to substitute to get the general solution. So the general solution for case 1 is x equal to c1 plus c2x. So we can show here that case 1 is a trivial solution. Then we proceed with case 2. And still same, we have to find the general solution. Then we get the general solution is c1 cos mu x plus c2 sin mu x. Then when we apply boundary condition, x double prime L, x prime L equal to 0, then we can get C2 equals 0. So it also have given us trivial solution. So we consider our case is case 3, which is lambda equal to mu squared lambda equal to 0. So from equation 2 just now, we have to integrate both sides, which is integrate t prime t over t equal to integrate negative k lambda. So we get this equation, then we can let e power of c equal to dn, then we let t this equal to equation number 5. We can substitute equation 4 and 5 into our first equation, which is uxt equal to xt. Then after substitution, we can apply boundary condition. Since exponent negative lambda kt not equal to 0, so we can get an equal to 0. Then after we apply boundary condition, we get this equation, then we have know that bn not equal to 0, so sin mu l equal to 0. So we apply boundary condition for the next boundary, which is ux0 equal to function, which is function summation of bn sin n pi x over l. So we can use Fourier sine series to get the bn and substitute the lambda n equal to n pi over l. So we have shown that bn equal to 2 over l integrate 0 to l function sine lambda n x in term of x, which is n is 0, 1, 2 and so on. Okay, that's all for me.
For the questions 1C, we need to use mapper to solve the problem. The questions given fx equal to x and L and k equal to 1. To evaluate Bn from the previous question, which is 1b, Bn is also given, which are 2 over L, 0 to L fx sine m pi over L x dx. So this is coding to find Bm, we just integrate and we get the answer. So this is the answer, Bn. And next for 2 Romans, 1C 2 Romans. In order to find first 5 coefficients in the series, we need to know the summation for the series, which are Bn sin n pi x over L exponent negative n power of m to the power of 2 and pi to the power of 2 over L to the power of 2. Multiply k and t. And this is the first 5 coefficient in the series, so we need to change n equal to 5. So this is we get 1, 2, 3, 4, 5. By varying k, we just need to change for k only. So this is for k1. So the graph we get, this is our graph. And for k2, the line that we use to net by varying k, we just need to change k only. So this is the graph we get when we change the k equal to 1. So next, this is the graph when we change k equal to 2. So we can see that the line slightly decreased from the previous one. So the next is also K3. The graph that we get, the line, there is no line here. So, and this is happen when we change k from the k equal to 3 to k equal to 5. So there is no difference from k equal to 3 to k equal to 5.
For question number 2, which is related with 1c, and the given this piecewise function, and suppose that x equals to 0, the boundary condition does not change. However, at x equals to L, the bar is insulated. UXLT equals to 0. And question A, determine the temperature UXT using this condition. So we consider the homogeneous linear PDE as this, and we need to use the method of separation of variables of products function x and a function of t, that is uxt equals to xt, and we need to find this to substitute in the homogeneous linear PDE, and we get like this. And dividing x over t, it will give us this, and we consider the negative lambda as a constant. From ODEs, from this function, we form the ODEs, and t prime plus k lambda t equals to 0, and x double prime plus lambda x equals to 0, and the boundary condition become u 0t is equals to 0, and when we substitute this boundary condition into this function, it will become into this function, it will become x0 equals to 0 for all t. Same goes to uxlt, which is equals to 0, and x double prime l equals to 0 for all t. In this case, we use case 3. It is because for case 1 and case 2, we will obtain trivial solution. So, where in case 3, where lambda greater than 0, so we let lambda equals to mu squared. And we substitute into this equation, and this we use auxiliary equation to find the m, and we will get m equals to plus minus I mu. So we will get the function of x equals to c1 cos mu x plus c2 sin mu x. This is from Euler, if I'm not mistaken. Okay, when the boundary condition x0 equals to 0, so we substitute into this function, we will get c1 equals to 0. So we will get x2 equals to c2 x equals to c2 sin mu x. When we use the boundary condition of x prime l equals to 0, we will get like this. So since cos mu l is not equals to 0, so cos n pi equals to negative 1 power of n, where mu l equals to n pi. Since pi over 2, 3 pi over 2, 3 pi over 2, and
it becomes so on until 2n minus 1 pi over 2 is equals to 0. So we can make conclusion that 2n minus 1 pi over 2 is equal to 0. And we mu equals to 2n minus 1 pi over 2 multiply with 1 over L, we will get this where n equals to 1, 2, 3. So we let lambda equals to mu squared. So lambda equals to this mu. Substitute back into this, we will get this. And where n equals to 1, 2, 3, and so on. So we will get C2 sine mu x, which is mu, this mu, substitute back into this, and we will get this. Hence, we will obtain xn equals to Cn sine 2n minus 1 pi x over 2l. From ODE, we need to find function of t. So we need to integrate because it has t prime. So we integrate with respect to t, and then we will get Tn t equals to dn exponent this. So substitute back. We already get xn and tn. So we substitute back in the equation ust equals to xt from the first equation that we get and that we so we combine the equation and we will get this. So we let an equals to cn plus dn and lambda n equals to 2n minus 1 squared pi squared over 4l squared. So the temperature ust we get is an sine 2n minus 1 pi x over 2l exponent negative 2n minus 1 squared pi squared over 4x squared kt. For the question 2b, repeat the problem in case 1c. We know that case 1c, we must use mapper to solve the problem. So, the question 2b, the piecewise we get from the question 2. So, in 1c, k is given, which is k is equal to 1. So we copy back again ust. Ust we get from the 2a. This. And after we copy, we must assume that t is equal to 0 to know the basic sign to substitute to an. So this we get an. An is the Fourier sine series. Next. After we know our an, from this is the equation from the piecewise, which is fx equal to x and fx equal to 1 minus x, like this. For the fx equal to x, x is from 0.5, which is 1 over 2 to 1. So this is the equation A1. This. Why we must search A1 and A2? Because we need to plus them in order to find an. So after we know a1 and a2, so we plus, so this is our an. This. Next, after we know the an, we can substitute to the uxt. So uxt we get like this. Sum an ni after we calculate from the previous. So this is an, we just substitute from to this, we just substitute to this equation. And this is equation from the uxt. So this is summation. And next, we have to know 5 coefficient term because we just repeat from the 1c. So this is coefficient 5 term, first 5 coefficient in the series. And next, this is the graph for the k if we assume k is equal to 1. So this is for k equal to 2. We get this graph, and we know that graph is decrease if k equal to, if k is greater than 1, this line will decrease to origin. So that's all.
Okay, now I will discuss about the difference between the change of boundary condition on the metal bar temperature in question number 1 and 2. So this is a graph on question number 2 and this is graph on question number 1. So let's see that in graph in question number 2, we found that when k equal to 1, the graph is slightly increased like this. But when k increase, when for example k equal to 2, so the graph slightly decrease slowly from previous k equal to 1, the graph like this. But when k equal to 2, the graph slow down, decrease, and like when k equal to 3, the graph always decrease until for the k equal to 5, the graph maybe exceed to origin. But in question number 1, the graph slightly increase on when when t equal to 0.2, but it slightly decrease when x at this 0.2 and slightly increase, but then they decrease again, and for the last it increased to t equal to 1, then drop into 0, x0 and t0. So same to when k equal to 1. So like this yellow area did not appear when k equal to 5. Let's see. This is k equal to 2, but the yellow is there. But when the k equal to 3, there is no at least have green, but it's not appear slightly. But when k equal to 4 and k equal to 5, the green did not appear at all. Compared to the question 2, when K is more larger, the green line will decrease, but not like that question number 1, which is not appear at all. So that's all that I want to discuss about two between the change of boundary condition on metal bar in question number 1 and question number 2. Thank you. Peace.